So another similar question. We're looking for corresponding measurements, and on here I can see the 10 and the 6. So I'm going to do a division now to get the scale factor. Now, sometimes that division is going to give you an awkward decimal, in which case you need to maybe use the fraction or use lots and lots of accuracy. So my scale factor is going to be 10 divided by 6. Now 10 divided by 6 as a fraction comes out as 5/3, and as a decimal comes out as 1.6 recurring. So I'm going to use the fraction this time because I want full accuracy. I'm going to be asked now to calculate the length of BC, which is this length over here. That corresponds to the 12 on the smaller triangle. So I've got to do 12 times my scale factor, 5/3. And that's going to give me a length of 20 on this triangle. Then I'm asked for the length of PR. PR is a length on the smaller triangle. So I'm going to take my 18 on the larger triangle, and I'm going to divide that by my scale factor, 5/3. So 18 divided by 5/3 gets me 10.8. This is a good example of a question where the exchange rates approach may well be easier and more intuitive for you. Now this question was a little bit sneaky because our two triangles overlap. So the trick here is going to be to start off by drawing them separately and very carefully. And I shall do that in the next video. In fact, no, let's do it now. So let's take this triangle ABC, the smaller triangle. I'm going to draw a little sketch of that over here. Doesn't need to be perfect. I'm going to label my 15 and my 12.5 over there. Now the larger triangle is from A to D to E, and I'm going to draw that triangle like this. Something on these lines. And this is where we have to be careful. The reason I did this is because I need to think about what these lengths are. In particular, this length over here is not just 6, but it's 15 plus 6. It's 21. Okay, so now that I've done that, I can see which sides correspond to each other. That's the 15 and the 21, and I can make a scale factor. So 21 divided by 15 will give me the scale factor, and that's coming out as 1.4. I want to work out the length from D to E, which is this length over here on this triangle. There's my corresponding side, so 12.5 times 1.4 will give me my answer. And that's coming out as 17.5 centimeters. Now this last question over here, well this last page of questions over here, is just a little bit different. Here we're being asked to show the two triangles are not mathematically similar. At the beginning of these solutions we said that similar shapes are ones connected by a scale factor, something which we could multiply and divide all the lengths of all the sides by to get the new shape. So the way we show that two triangles or two rectangles or two circles are not mathematically similar is to look at the scale factor between corresponding sides and then do it again for a different pair of corresponding sides. For similar shapes, these answers will always be the same. These scale factors will always be the same. And for non-similar shapes, they won't. So, the 20 € note is a rectangle 133 millimeters long, whereas the larger note is 165 millimeters long. So if I do 165 divided by 133, I get that scale factor. And that's coming out as 1.2406, and then a bunch more stuff. But of course I have a different pair of corresponding sides. The 72 width for the smaller one, and the 82 width for the larger one. 82 divided by 72 should also give me the same scale factor if they're similar. 82 divided by 72 gives me 1.138 recurring. So as these are not the same, as these scale factors are not the same, the two rectangles cannot be similar. Okay, so that's a little bit of a variation on the question. And this is a good example of a question where we need to be aware of the concept of a scale factor. In all the previous questions, I could use the idea of exchange rates to do the work. And that's great, and for some of them, even better than using a scale factor. But we cannot forget about the idea of a scale factor in case we're asked about it directly, or indeed in this case where that idea is the key to unraveling the question. So feel free to use the exchange rates method, but don't forget about the scale factor that pins the thing together. And as last question, we're simply asked to identify some shapes which are congruent and similar. So I'm going to just reduce the size so we can see the whole thing. Congruent means exactly the same. So I'm looking for another shape on this grid which has exactly the same configuration as A. Now it could be rotated around, that's absolutely fine. And if I look down here at G, we can see that's the same shape as A, it's just been rotated around. So the shape that is congruent to A is G. Now I want to find another pair of shapes that's exactly the same as each other. And they do have to be exactly the same. And looking on this grid, I can see that the L shape over here of D is the same as the L shape over here of I. It's just again been rotated around, in this case 90 degrees. So D and I are congruent. Now if I'm looking for a shape that's mathematically similar to B, I'm looking for a shape which is like B, but it's been enlarged with a scale factor. Now it might be tempting to go down here. Hopefully we can rule out, of course, E and C straight away, right? It might be tempting to look at H. It looks 2 times longer, but because that scale factor hasn't been applied to the width as well, it can't be similar. This leaves us with F. F is 2 times longer, and it's also 2 times wider. It must have the same scale factor in both directions, which is the idea we were exploring in that banknote question. So F, because it involves that scale factor 2 in both directions, is mathematically similar to B. And that concludes the solutions for the similarity worksheet.